Another generalization that we find, where the landscape consists of a moraine, that gravelly deposit formed at the edge of the ice. Where there is a moraine across the valley, beneath that moraine we will find gravel. And typically interfingered with that gravel down valley we'll find lake deposits. This is one of the environments we see in the modern analogs today. And we have modern examples from well data to point out that in fact this generalization has credibility. The nature of the landscape on these moraines is such as this, photograph taken at Index, just a few miles south of Cooperstown. Classic morainic topography consisting of rolling hills. And then down valley, which is the direction in which you're looking, the topography gets a lot flatter down here because that's the outwash surface. This sort of a landscape can be interpreted to have gravel at depth beneath the moraine, gravel at depth beneath the outwash. And therefore, we want to stay away from these locations if we have land use development with a potential for contamination. It's through these gravels that a high degree of recharge will occur, and it's beneath these that the major aquifers exist. And here's the nature of the deposit within the moraine. It looks an awful lot like the kinds of deposits you find within the outwash. Typically, we teach our students that moraines don't contain these sands and gravels, but in central New York they do, and I won't get involved with why, they just simply do. Therefore, we have to treat the moraines like we do the outwash surfaces as potential locations for groundwater contamination. Lastly, in the generalizations that were provided by McNish and Randall, you see a landscape that may look a bit complicated to you, and rightly so, because it's a landscape that has very little predictability. These are the landscape surfaces as well as the layers of material at depth that form in regions where the glaciers ceased to be active and stagnated in place. Without getting involved in the esoteric aspects of whether glaciers actively flow or stagnate, suffice to say that when they do stagnate, they create characteristic landscapes to tell us that they stagnated there, and they create a subsurface stratigraphy that is absolutely chaotic. It's non-predictable. Unlike the other cases I've shown you, where I feel very confident telling you that there's sand and gravel at depth below outwash, or sand and gravel at depth below a moraine, or silt deposits beneath a lake surface. I wouldn't hazard a guess as to what would lie beneath the surface of a dead ice topography, because practically anything can, and it's non-predictable. One of the things that we know about this, one of the good things about this is that knowing that there's a lack of predictability provides a piece of information that's useful later, as you'll see. Here's a cross-section of a place in which the ice stagnated. And at best, we see a single example here. We see nothing that's characteristic of the next place where the ice stagnated. These turn out to be one of the real knotty problems in glacial geology today, and one of the things we're working on most energetically now. We know these deposits formed in places where the ice stagnated because the deposits show evidence of being collapsed as the result of being let down when buried ice melts. One of the modern analog photographs I showed you indicated sand and gravel burying blocks of ice. That was the case here as well. The layers of sand and gravel that look wavy in this photograph originally were deposited flat. But when the ice beneath this melted, they subsided and fell into these collapsed and chaotic positions. Well, concentrating our efforts now on places that are less predictable so that we know more about them and can be more predictive in the future, we look at these dead ice locations, and here's what we see. I will not go into the details involving this, except to say that the condition that would have existed to produce the various landscapes on the right side of this are the conditions we see on the left side. In each case, a large block of ice is left behind and buried under sand and gravel. When I say large, I mean it's as wide as the valley is wide and can be hundreds of feet thick. Inordinately large, larger than postulated in the past. But now we have evidence to prove that these huge detached blocks of ice did exist. Part of the evidence is in the landscape. The valley floor will have a big hole in the bottom of it, so to speak. The normal landscape produced by glacial retreat is interrupted by this huge hole labeled here as a sink, a dead ice sink. And I'm happy to say when the research was done to begin to develop these ideas, one of you in the audience helped me do this. The dead ice sink can be seen here in three different situations. They are by no means the only situations in which they occur, but rather shown here to illustrate the fact that they're more common than we previously thought. Why are we concerned about this, and what's important about it? The important thing is that when we look at this from top to bottom, the progressive development of a dead ice sink, an anomalously big hole in the floor of a valley, we find that it originated when meltwaters from the ice carried sand and gravel deposits over a buried block. And progressively with time, as the glacier retreated and eventually retreated from the area totally, so that the last of the meltwater flowed across the surface here, the ice persisted for 1,000 years, maybe 2, maybe even 3. There's good evidence to tell us that buried ice can exist in the modern locations of the world for 2,000 to 3,000 years. Therefore, long after the glaciers receded, this ice could have persisted. Later on, after the discharge through this valley was only that of melting snow and rain, the normal discharge of today, and not that charged by meltwaters, and that ice melted, the hole developed. And that hole contains, and here's the part that's important for aquifers, that hole contains deposits that were collapsed down from above. Collapsed down, disoriented, even broken, quite heterogeneous in their nature, and when we're finished here, and you're looking at a down valley cross-section from left to right at down valley, groundwater that normally would move down valley to recharge these gravels would have to get through these deposits first. And because these are terribly variable and may not have the same hydrologic conductivity as the gravel up valley, not as much recharge will occur down valley. We have to prove this now. This is an interpretation. And in the modern landscape, this is what a dead ice sink looks like. Here are the steep valley walls. This yellow surface is outwash, filled in by meltwaters. Over there, the yellow surface is outwash, filled in by meltwaters. Down here, the same. And in the middle of all of this, a hole which, by normal, ordinary, non-dead ice processes, should not have originated. But it's here, and it's the dead ice terrain that results from buried blocks. The landscape on this is rather unspectacular. It is, you're looking at the surface of a dead ice sink at the place where that map illustrated a moment ago. And the surface out here on the floodplain is part of that dead ice sink. Drilling a hole in here would produce unpredictable results. Well, in summary, we can look at these things in perspective of what the glacial geologist is most concerned with, and that's the regime of the retreating glacier. These are terms that pertain to the interpretation of a glacial geologist's history of the area. Here's the part that's interesting to hydrologists, hydrogeologists, the stratigraphy, the nature of the layered materials that lie at depth that originate at in these different regimes of retreat. This is the activity of the retreating glacier, and out here the landforms that develop during each of these activity sequences. So, this type of material will lie below those sets of landforms. This type of material beneath these. And in this way, an understanding of glacial geology and application of it can be useful in the identification of principal and primary aquifers and the potential for their recharge, and also guide us in land use planning to avoid the potential contamination in areas where groundwater is recharged most suitably. Thank you.